Hi, in this video, we want to take a look at the normal distribution. We want to first confirm that it in fact gives us a probability distribution, and then we're going to take a look at the central limit theorem. Then we're going to apply the central limit theorem by approximating a binomial distribution. Okay, so let's go ahead and let's double check to make sure that the bell curve, the Gaussian curve, the normal curve, in fact gives us a probability distribution. Okay, so anytime I have a non-negative function that integrates to a finite value over the entire real line, then we can always rescale it to give us a probability distribution. That is, it has to integrate to 1 when I integrate over the entire real line. All right, so the two things we need to check is, first, it's never a negative value for the function. Second, we have to check that the integral is in fact equal to 1. All right, well, I look at this 1 over the square root of 2 pi. That's a scalar. Okay, a constant value. And then I look at the e business. Well, I know that e is always positive. Therefore, yes, this is always a positive function. So now I need to show that if I integrate from negative infinity to positive infinity over the function, then I will get the number 1. Okay. Well, let's try like make this a little bit easier of a problem. Let's relax it a little bit. Instead, I'm going to look at just the core aspect, the kernel of the function. And I want to show that the integral of this is equal to the square root of 2 pi. Okay. Well, now there's going to be a trick. And if you didn't know this trick, you probably wouldn't think of this trick. I'm shifting around because the sun is in my eyes. Trying to get some shade from the tree. Okay, I'm going to invoke a trick. And I know what that trick is. If you've never seen this trick, you'd be like, oh, I would have never thought of that. But I know it, so it was presented to me when I was a student, and I'm going to do exactly what my professor did. Okay, so I want to show that this integral is equal to this square root. Okay, well, this integral is going to be a number, all right? So realize that since I am integrating with respect to x, from negative infinity to positive infinity, when I'm done, I'm not going to have any x's in this. So this is, in fact, just a regular old number. Okay, since that is a regular old number, this square, if I square the whole thing, that's going to be a number. Well, if I'm doing everything right, showing that this square is equal to 2 pi is equivalent to showing that this integral is equal to square root of 2 pi. Okay. Now, something I need to say. Why is it that I can use standard normal for this? You'll notice that when I started with this, I'm using mean 0, standard deviation 1. All right, remember that from the location scale property of the normal distribution, I can do a location scale transform. I can multiply by a constant, add a constant to any normal random variable, and I get another normal random variable. Okay, so that means that if I work this out for standard normal, I can do that location scale transform, and I can get any other normal distribution. So by proving that I get what I want on the normal distribution, I prove it for every single normal curve. Okay, kind of powerful stuff. Now, let's go back to the squaring business, because it's hip to be square. All right, well, this square is equal to the integral times the integral, right? Now, what I'm doing here is I'm just changing the variables. I'm changing the variables. It changes nothing because everything inside the parenthesis, when I'm done with the integration, it doesn't matter if I represent the variable with a z, an x, a y, a u, a delta. It could be any letter I want. It's going to give me the same result. So it's okay for me to take the two integrals here and just represent them with different variables. Okay, so now, if you remember your multivariate calculus, when I look at this, I notice that here I have no u's going on in this integral. I have no t's going on with this integral. So this integral is a constant with respect to everything going on here, and this integral is a constant with respect to everything going on here. That means that I can do I can like distribute the integrals inside of each other without messing things up. If I had a u inside this integral, or if I had a t inside this integral, it would get more technical. But here it works out to be the easy case. This is like the easy type of calculation in Calc 3. Okay, so when I do that, I'll get a double integral of this two variable function dt du. Okay, so now I notice that, well, I've got e and I've got e and I've got exponents, so I'll just go ahead and use addition to put them together into one exponent. All right, so now I look at this, I have something squared plus something squared. I look at that and go, well, isn't there like a formula like x squared plus y squared equals r squared? Yes, yeah, there's a circle formula from college algebra. All right, so what I'm going to do, I mean, you know what? That looks a lot like a circle, so I'm going to use polar coordinates. All right, so what I'm going to do is I'm going to replace t with r cosine theta. I'm going to replace u with r sine theta, like this. Now, so when I do a substitution, if I have just single variable, that's, I'm going to be using a derivative to work it out. I'm in the multivariate case. So you see that the relationship between t, r, and theta, u, r, and theta, is a little bit more complicated than in the univariate cases that we've looked at. Okay, so I need a Jacobian. So what I need to do, I need to set up this special matrix where I take these terms here and I take derivatives with respect to r, I take derivatives with respect to theta, I put them on the matrix and in the right format. All right, so here's my Jacobian. Then I take the determinant, and what I'm going to do, I'm going to multiply on the inside by my determinant here, r, just so that things work out. So remember, the determinant is going to be cosine, r cosine, multiplied together, then minus sine theta times negative r sine theta. All right, so in this part, I get r cosine squared. Here, I get negative and negative is positive, r sine squared theta. So I have r cosine squared plus r sine squared. Well, remember, from trigonometry, r squared plus sine squared always equals 1. So if I factor out the r, I see that I just end up getting this r by itself. All right, so now I'm going to go ahead and do my substitution. I replace the t with r cosine theta. I replace the u with r sine theta. And then I tack on an r, and I replace t and u with dr d theta. But wait, there's more. Okay, so when I'm dealing with this r business, what values of r could I have? Would it make sense to have a negative radius on a circle? No, it wouldn't. So my integral changes, the bounds go from 0 to infinity. Now, theta is an angle. Theta goes from 0 to 2 pi. I could also do like negative pi to pi or something like that. It doesn't really matter. But I chose 0 to 2 pi to make it simple. All right, so now I go ahead and I simplify some stuff. So here I'm using cosine squared plus sine squared equals 1. And I notice that this r is almost the derivative of the exponent. I'm just missing a negative sign, which makes my integration super easy. And just work it out, and boom, I've got that the square of the integral is equal to 2 pi. Well, that's equivalent to the integral being equal to square root 2 pi, which was what we wanted, because now that connects back to the integral being equal to 1. Okay, so now let's talk about the central limit theorem. The central limit theorem is super powerful. All right, so it works out that if I take, if I take an average of values, if I take a sum of values, a lot of times I can, really well approximate it with a normal distribution if I have a larger data size. All right, so we really use this when I'm working with averages. This is when it's like super important. If I'm working with averages and I don't know exactly what the distribution is, chances are I can approximate the distribution of an average with the normal distribution. This gives me a lot of weight. So how we use this is that I see that I have an average going on in real life data. I need to assess something. I don't have complete information, because remember, if you're using data, you don't have complete information. If you knew what was going on, you wouldn't be working with data. Okay, so I have an average. I need to make a conclusion off of it. Well, if I knew the probability distribution, I could use that to guide some decisions. Well, the central limit theorem says that I can use the normal distribution to approximate the distribution of that average, and I'm in a very good position. Okay, so let's say that all these x's are independent, identically distributed. They all have expected value of mu, and they all have variance of sigma squared. Okay, so independent, identically distributed, expected value of mu, and finite variance, and they all have the same variance. Then I'm going to be able to use the normal distribution to approximate the average. So we'll say x bar is equal to the sample average. Let's say u sub n is equal to x bar minus mu divided by sigma times the square root of n. Then the probability that u sub n is between a and b, it will go to this integral as n goes to infinity. So what we're saying is that the distribution, the probability distribution of u sub n converges to standard normal as n goes to infinity. So if I have a large sample size and I take an average under these assumptions, it's okay for me to use the normal distribution. And the bigger the n, the better the approximation. Now, I'm not going to prove this. The standard proof for this uses moment generating functions and Taylor's theorem, neither of which we have gone over in this video series. All right, so let's go ahead and take a look at this as actually using it. Let's say that I have a large number of trials that are Bernoulli. And so, and they're independent, identically distributed. And I'm working in a situation where the computations are kind of ugly. So remember that if I'm looking at the binomial distribution, I have those, n choose k, I have those factorials going on. Factorials can be hard to work with if I have to actually actually compute for large n. All right, so if it's kind of difficult to work that out, I would like a faster, easier way to go. So what I'm going to do, I'm going to approximate the binomial distribution using the normal distribution. All right, so how can I do that? Well, binomial is a sum, which means that if I divide the binomial variable that I get by the total number of trials, that's an average. If I have an average, independent, identically distributed, and a decent size of n, then I can go ahead and use the normal distribution to approximate it. So what I'm going to do, I'm going to treat that n as a scalar, and then I'm going to treat my random variable as n times x bar, and so then I can proceed. All right, so the expected value of x bar is the expected value of 1 over n times all of the x's added together, which gives us p. All right, and then the variance of x bar is the variance of 1 over n times the sum of the x's. That comma should not be there. And so since I have independence between my observations, I can break up the variance. And so we can see that the variance of the average from Bernoulli data is going to be, the variance of Bernoulli divided by n. Okay. So now what I'm going to do is I'm going to work with n times x bar because that's the actual binomial random variable. So what's going on is the sum of x's is the sum of Bernoulli's, that is binomial. To be able to get to that distribution with the normal distribution, I have to take an average. So I'm taking the average and then multiplying by a constant, so that because when I'm dealing with normal, I can do that. And so now I can proceed as I would like. So what I'm going to do is I'm going to approximate the binomial random variable minus its expected value divided by its standard deviation. And that's going to be approximately normal. Now, something that is critical about this. So remember, I said the limit as n goes to infinity. The limit as n goes to infinity. N is going towards infinity. I can't reach infinity, right? I mean, it's a big number. It's really, really, really big. Okay, so we can do this as long as n is greater than 9 times the maximum of the ratio between P and 1 minus P. As long as this is true, this will be a reasonable approximation. Okay, so now let's go ahead and work out some details. So how do I actually get normal distribution to execute this for us? Well, let's say that I want the probability that my binomial random variable is equal to a particular value. All right, well, what I'm going to do is I'm going to change this up. I'm going to make this into the probability that the value minus a half is less than B, which is less than I plus 1/2. Okay, why am I doing this? Well, binomial random variables always take whole number values, correct? So if I say the probability of 5, well, that's going to be the same as the probability of greater than 4.5 and less than 5.5. All right, so I get the same exact probabilities either way. Now, why do I actually invoke this step? Well, what's going on is that when I deal with the normal curve is continuous. And since it's continuous, I need to like kind of spread things out to be able to get this discrete value taken care of. Okay, so what I'm going to do, I know that I need B minus expected value divided by standard deviation. So I'm going to take this, I'm going to take the inside here, I'm going to subtract by NP, and then I'm going to divide by the standard deviation of the binomial random variable. And so I do that here. I subtract by NP, subtract by NP, subtract by NP, and then divide by the standard deviation each time. And all right, this line is, I did not want that there. It's not incorrect, but it doesn't work out. And so we're going to approximate. This should be an approximation. We will approximate this with a standard normal random variable. All right, so let's verify that this actually works out. Okay, so what I'm going to do, I'm going to set n equal to 30, p equal to 1/2. You know, I just kind of randomly pick those. So n is equal to 30, p is equal to 1/2. And so that satisfies that 9 times the maximum of p over q, q over p. So p over q, q over p are both equal to 1. And, you know, so n is definitely greater than that. All right, and so I want to look at all the probabilities from 0 to 5. So I'm going to use the binomial distribution to get, now here, this is the actual correct values. They're going to be stored in VD binom. Now, what I want to get an approximation. To get that approximation, what I'm going to do, remember that I had like in my inequality, I have an upper part and a lower part. What I'm going to do, this is, I'm going to go along the Gaussian curve, and I'm going to chop up intervals so that I can make like sub-regions. And each sub-region will be centered around an integer value. So I'm going to take the probability from the value minus 1 to the value plus 1 and go through and work it out. Now, I'm not quite doing it the same way I wrote it in the theory, in the derivation, because I can go ahead and put mean and standard deviation right here to take care of it. And so now, to get the actual value, remember that the p norm gives me the probability of less than or equal to a value. So to get the probability of 5, let's say, I have to take 5 plus a half, the probability of less than or equal to 5 minus a half, and then I subtract off the 2. And so now let's go ahead and look at the distribution of the actual correct probabilities. And so here, these are the correct ones. Now this is from binomial random variable. That looks a lot like a bell curve, right? All right, so this kind of confirms that what we're doing makes sense. Now let's look at the approximations. I cannot visually see a difference. There is a difference though, but I can't see it. All right, well, let's go ahead and let's take a look at what is the actual error. So for the error, I'm taking the difference of the two values and I'm going to plot them. And so we can see that, so the most important thing to look at is the magnitude of these numbers. This is the y coordinate is in scientific notation, and I have to the power of -4 for the extremes. So the error is very, very small. So for this problem, for my applications, this is close enough. And so we can see that's, I mean, it's pretty tight. And just to put it on one scale, I use ggplot to put the three of them together. So here's the approximation of the probability. Here's the correct probability. And if I subtract, you can barely see it down here. There's just a little bit of blue. There's a little tiny bit of blue right here. And that is the actual difference between the approximation and the correct value. So this confirms that using the normal distribution to approximate binomial is a good idea. And so for situations where computing like those n-choose-2 values, when I get more complicated binomial stuff, it's just better to go to the normal distribution and with a tiny little bit of error. In fact, if you look at the binom test and the prop test in R, the prop test uses the normal distribution for binomial data. The binom test uses binomial data. All right, well, that's all I've got for you. Take care and goodbye.